Hi, in this video, I'm going to go through the AQA Chemistry A-level paper. This is the 2021 paper, and it's paper one. I'll probably do this in 3 separate parts. It's quite a long paper. Okay, so the first one we have got, the first question is about the Born-Haber cycle. Okay, and all right, so here we go. Question one. State the meaning of the term enthalpy change. This is a question that comes up not very often, every now and again, and lots of people get it wrong because what it means, the strict definition of enthalpy change is the energy change at constant pressure. You need the constant pressure bit. Okay. Right, the next part of the question is the Born-Haber cycle. Right, so what we've got to do for the first bit is question 1.2. We've got to fill in the missing formulae and put in state symbols. And then the next bit, 1.3, we've got to put in the values and calculate a value for the lattice enthalpy of formation. Okay, so let's do this one here. Well, we can see we've got calcium as a gas there. Standard state of calcium is a solid, so you've atomized the calcium in that first one, so it's calcium solid and chlorine gas. This step, obviously, we've first ionization. This step will be the second ionization, so we're going to have calcium as the 2+ ion there. I've got 2, and that's a gas. 2 electrons, and we haven't done anything to the chlorine, so that's just as Cl2 gas. Right now, so we have on this step here, we're going to see electron affinity, so we're going to turn the chlorine atoms into chloride ions. So it's calcium 2+ gas plus 2Cl- gas there. Right, now let's go on to this next bit, 1.3. We've got to put the values in to calculate this line here, which is with the arrow going up. That is the lattice enthalpy of formation. We are forming, dissociation. We are breaking up the lattice and turning it into gaseous ions. The arrow going up is going to be endothermic. Now we can see here we've got negative and positive values given here, but the whole point of drawing a Born-Haber cycle is because we're drawing it as a diagram. Going up is endo and going down is exo. We don't really need to put the signs in and worry about them. Okay, so right, this first bit here, what we're doing there, that's the enthalpy of formation. We're forming 1 mole of calcium chloride from its elements in the standard state, so that's -795 there. This one here, what we're doing is the first ionization energy of calcium, so that is going to be that's 590, and the next one is 1150. That's a second ionization into, that's 590 and 1150 there. So I missed what this one out with this one here. What we're doing, we're atomizing our calcium. So first, the atomization of calcium, that's +193. This one here, we've got to be careful of because we are forming we're forming 2 moles of gaseous atoms of chlorine, right? So it is double the atomization of chlorine, double that. So we multiply that by 2, that's going to give us 242. Okay, and that's a very common mistake. People think that don't realize they have to double it. Okay, here the electron affinity, we have to remember to double that. So what we've got here, we have got the first electron affinity of chlorine is 364. We're going to double that, so that gives us what, 728 there. Okay. Right. So what we're now going to do is we are now going to add up this lot all together, and that gives us add all that together. I work that out to be 2970. Again, I'm ignoring all those signs, the negative and positives, because I've drawn it as a diagram. Okay, And we see we've got 7 to 8. So that means this bit here, the bit we're interested in, all we've got to do is subtract this 728 from the 2970. So that's 2970 minus 728. And that gives us a value of 2242. And that is the lattice, that's kilojoules per mole. That's the lattice enthalpy of dissociation. Now we've got to determine the arrow, the sign there. Now, because our arrow is going up, that's endothermic, so it's a positive value. So that is our answer there, plus 2242. And if anyone is going to make a mistake there, I would have thought they would have made it on this bit here, where they don't realize that the enthalpy of atomization is when you form 1 mole of gaseous atoms. We're not forming 1 mole of gaseous atoms, we're forming 2 moles of gaseous atoms there. So you do need to double this value here. Okay, that's that Born-Haber cycle question then. Okay. Okay, so this is going to now move on to enthalpy of solution and so forth. Right. Magnesium chloride dissolves in water, given an equation including state symbols to represent the process when the solution of magnesium chloride, enthalpy of solution of magnesium chloride is measured. So we're going to have magnesium chloride solid, and you're going to dissolve it in water to form magnesium 2+ ions, state symbol aqueous, plus 2 moles of chloride ions, and they're going to have a state symbol of aqueous as well. You could probably get away with not doing that as ionic, but I think that's the best way of doing it. Right. Table 2 now shows some enthalpy data. Right. And use your answer to question 1.4 and the table to calculate a value for the enthalpy of solution of magnesium chloride. So, right. So I'm going to write down that equation again here. So we've got magnesium chloride solid, and to dissolve it to form magnesium 2+ ions, 2 chloride ions. Now, when we're doing these, working out the enthalpy of solution, okay, the third thing in your Hess's law cycle that you want, so the third thing you want down here is going to be the ions as gaseous ions. So I'm going to write down Mg2+ gas there, and 2 chloride ions gas there. Now let's have a think about although I'm going to draw those arrows here. So let's draw this in red. This red arrow here, what we're doing, well, we're turning 1 mole of ionic lattice into gaseous ions. So that's going to be the lattice enthalpy of dissociation. Okay, so that's going to be plus 2493. And then what we're doing in this one, we're getting gaseous ions, we're turning into aqueous ions. So we're hydrating them. So we're hydrating 1 mole of magnesium ions. So that's going to be minus 1920. And we've got 2 moles of chloride ions there, so that's going to be 2 times minus 364. Add that lot up together, and it comes to 2648. Okay, minus 2648. Now we are interested in working out this value here, delta H. This is delta H solution. The enthalpy will change when you dissolve 1 mole of the solid into gaseous ions. So now we can see here the Hess's law cycle, delta H sol. Well, we're going with the red arrow there, so that's going to keep its sign. And then we're going to go up there. We're going with the green arrow, so that's going to keep its sign as well. So delta H sol is simply then going to be plus 2493. And add on the minus 2648. Work that out. That comes to minus 155 kilojoules per mole. Okay, that is the answer to that. There is our 2 marks there. Okay, so move on to the next question now. Okay, the enthalpy of hydration of calcium is minus 1650. Why is this value less exothermic than magnesium value? The magnesium value they told us was minus 1920 for magnesium. Well, it's because look at the periodic table. You've got magnesium, and then you've got calcium below that. Calcium is a bigger atom, so the calcium ion is bigger than magnesium. So Ca2 plus is bigger. Got the same charge though, so the charge density is lower. Now, why is the hydration exothermic? Well, it's the attraction between the negative oxygen atom on a water molecule and the positive ion. So the attraction to the oxygen in the water molecule is going to be weaker because the charge density is lower. Okay, now on to question 2 now. Question about atomic structure. Define the mass number of the atom of GCSE, isn't it? So it's simply the number of protons plus the number of neutrons. Okay, pretty straightforward. Right, now we have got one sort of subatomic particles. Again, there's not really much here that you don't do at GCSE. Well, look here, the atomic number of titanium is 22, so it's going to have 22 protons. Well, they tell us that anyway. Right, 46 Ti, 46 Ti, number of neutrons. How are we going to do that? Well, that's going to be 46, the mass of it, minus the number of protons. So that's going to be equal to 24. The 49, it's going to be 49 minus 22, which is going to be 27. Number of electrons in those species, well, this is neutral, so the number of electrons is equal to the number of protons, 22. This has a double positive charge on it, so it's missing 2 electrons, so that's going to be 20 electrons for that one. Okay, so now we have been working, so it's a one involving working out the relative atomic mass, because that's a bit easy, just working out the relative atomic mass with the abundances. They tend to make us do things backwards. This is a bit of a tricky one, not as far as these questions go. They try to make it more difficult. Okay, so we know this, they tell us the ratio of abundance of the isotopes here is 2 to 1, but what they don't tell us is the abundance of the 48. So let's say the 48, let's call that X. So the abundance of the 48 isotope is X. Right, now what we're going to do, the normal thing is, right, the relative atomic mass, which is 47.8, is going to be equal to the mass of each isotope multiplied by its abundance. So we're going to have 46, and the abundance of 46 is 2. It tells us there, yeah. So you're going to have 46 times 2. Plus the abundance of 47. And that's 2 as well, is it? Yep. Plus the abundance of the 49, which is 1. So that's just 49 multiplied by 1. and the abundance of the 48. Now we don't know that, but we call that X. We're going to call that 48X. And we've got to divide that by the total abundance. Well, what's the total abundance is here, look. Total abundance is 2 plus 1, 2 plus 2 plus 1 plus X. And of course, that is equal to 5 plus X. So that's going to go on the bottom line there. Right, so I'm just going to simplify. So 46 times 2, I'm going to rub that out, and that becomes what? 46 times 2 gives us 90. 46 times 2 is 92. 47 times 21 times 2, sorry, is 94. 49 plus X. Okay, so multiply both sides of the equation by 5X. That's going to go on the top line. So 5 plus X, sorry, multiplied by 47.8. So just evaluate all of that. Then we end up then with 5 times 47.8, that's 239 plus 47.8x, 92, 94, 49, that gives us 235 plus 48x. Right, subtract 235 from both sides of the equation. We are going to get 4 plus 47.8x is equal to 48x. Subtract 47.8x from both sides of the equation. We get 4 is equal to 0.2x. Divide both sides of the equation by 0.2, we get x is equal to 4 over 0.2, which is equal to 20. So the abundance of the 48 is 20. It's a lot more abundant than the other two, which makes sense, okay? Because, you know, the average value is very close to 48. The abundance of the 48 isotope is equal to 20. Right, so what's the total abundance of the isotopes then? Well, the total abundance of the isotopes, right, let's rub this out up here. We have got right, that's equal to this lot here, 5 plus 20, which makes 25. Okay, now the question is asking the percentage of abundance of the 46. Well, the abundance of the 46 there is 2, isn't it? So the percentage of abundance of 46 is equal to the abundance of 46, which is 2, over the total abundance, which is 25, multiplied by 100. Work that out, we get it is equal to 8%. Okay, so a little bit more involved than most of those questions, but I think it's because they're quite easy. They don't have to try and slightly new takes on it to try and make it a bit harder. There's not really much chemistry there. It's just a little bit of algebra. Right, let's move on to the next question. Right, this one is the period 3 oxides. Okay, so a lot of straightforward recall going on here. An equation for the reaction of phosphorus 5 oxide, sorry, that's P4O10, yeah, with water. Okay, now you should know that when phosphorus 4 oxide reacts with water, you get phosphoric acid. Okay, so we've got to balance that equation. Well, we've got 4 phosphoruses on the left and only 1 on the right, so we've got to put a 4 there. That means we've got a total of here 4 times 3 hydrogens here. That's 12 hydrogens, so that means we're going to need 6 waters. Just check our oxygens are okay. Well, we've got 10 oxygens there plus 6 there makes 16. And we've got 4 times 4 makes 16, so that's balanced. pH of the solution formed, well, I usually say 0 for that, because phosphoric acid is a strong acid and you're going to have quite a high concentration of it. I think in the mark scheme it says allow anything between -1 and +1. That's the pH of the solution, a strongly acidic solution. Okay, explain in terms of crystal structure and bonding why silicon 4 oxide, SiO2, has a higher melting point than phosphorus 5 oxide. Okay, so you need to know that SiO2 is a giant covalent structure. So when you melt it, you need to break covalent bonds, which is strong. Always worth saying that. So that means you need a lot of energy. Right, let's contrast to the situation P4O10. P4O10 is a simple covalent molecule. So when you are melting it, simple covalent, all you are breaking is intermolecular forces. In this case, they are going to be van der Waals forces, okay, which are going to be quite weak. So all you're breaking van der Waals forces, they're weak, and you don't need much energy for them. It's always worthwhile putting these questions when it's about melting point. It seems obvious, like if it's a strong bond, you've got a lot of energy, but people don't bother writing in a lot of energy. And quite often, not always, but quite often in the mark scheme, it says you do need to write that. So probably good habit to get into, just always write that. Okay, so question 3.4. An element in period 3, forms an oxide that is insoluble in water. Well, we've had, that could be aluminium oxide, which we've just had, or it could be which we haven't had, or it could be SiO2, which we've just had. Now, this oxide reacts with sulfuric acid and aqueous, so it reacts with an acid and with an alkali, so it is amphoteric, so it's got to be aluminium oxide, hasn't it? So it's Al2O3, and it wants an equation for the reaction with sulfuric acid. That's easy. It's a lot easier, the equation of aluminium oxide reacting with the acid rather than the alkali. So anyway, so it's going to be H2SO4 there. Here, the aluminium oxide behaves just as a standard metal oxide. It's basic, and so it's going to form a salt. So the salt is going to form, of course, sulfate is SO4 2- ion, whereas aluminium forms an Al3+ ion. So the formula of aluminium sulfate is going to be Al2SO4 3. We're also going to form water, salt and water when you have a metal oxide and an acid. So we just need to balance that. The aluminium's okay. We need 3 in front of the sulfuric acid to provide 3 sulfates. That means we've got 6 H's, so that means we're going to form 3 water molecules. And if you check, yeah, those 3 oxygens are coming from that, from the aluminium oxide there. So that is the easy reaction of aluminium oxide. The difficult one, of course, is the reaction with the hydroxide. Okay, but they don't ask us for that. Okay, the formula of a hydroxide of an element in period 3 used in medicine. This is going back to group 2 from year 12 stuff. It's magnesium hydroxide can be used as an indigestion remedy, okay, because it's basic, but it's not very soluble. You couldn't use sodium hydroxide for that. It's very soluble and it'd be very alkaline. So magnesium hydroxide is almost completely insoluble. Again, that knowledge comes from group 2. The group 2, you need to know the solubility of the group 2 hydroxides and the group 2 sulfates, which is year 12 stuff. Identify the element of period 3 from sodium to chlorine that has the largest atomic radius. Well, I've drawn it here. So I've drawn the periodic table here. Right, it's going to be, so we're talking from sodium up to argon. Well, just the chlorine, because okay. It's going to be sodium because, right, sodium has got the weakest nuclear charge, isn't it? They're all, it's quantum shell 3 is being filled here in all of them, so that's the same, but the electrons are held less tightly in the case of sodium because the nuclear charge there is the weakest it can be for an element in period 3. So sodium is our answer there. Okay, this is about iron, and its ions. Okay, right. First bit is a 6 marker on discuss the role of a heterogeneous catalyst in the Haber process as iron. Okay, so this is a pretty straightforward recall question, really. Nothing too difficult about that. Right, so right, a heterogeneous catalyst, we've got to state the meaning of that. What's a heterogeneous catalyst? Right, the catalyst and the reactants and products are in different phases. And it is nearly always the case that the reactants are gases and the catalyst is actually a solid. And I think we need to define the term catalyst here, so it increases rate of reaction by providing an alternative route. With lower activation energy. Right. What we're going to say next then, how iron acts as a heterogeneous catalyst. Well, how do all heterogeneous catalysts work? We need to say that the reactants adsorb on the surface of the catalyst. Okay. Okay, and that is very vague here at A level. You need to know this weakens the bonds. I would definitely say that and really explain how it does. And that enables the reaction to occur. And then we need to say the products then leave the catalyst, they desorb. From the catalyst. Right, and then we say the factors affect the efficiency. Okay, so what we're going to have to say here is for the catalyst to be efficient, it needs a large surface area. Right, and the lifetime of the catalyst, well, the catalyst can be poisoned. And in this case, the Fe will react with H2S. That's obviously going to form iron sulfide on the surface, and that means that the iron itself is not available for the reactants and products to bind to. Okay, so now let us move on to 4.2. This is about a homogeneous catalyst, iron Fe2 plus ions catalyzing the reaction between peroxide of sulfate and iodide ions. Now, this reaction is on the specification. It's quite a difficult thing here, but they ask the same question every time. It's actually on the specification, and you just got to basically know this example. And it's a straightforward recall of knowledge, really. Explain why this reaction is slow before the catalyst is added. Right, the reason is because they're both negatively charged. The peroxide of sulfate ion and the iodide ion are both negative, so they're going to repel. Right, now I'll give two equations to show how the Fe2 catalyze 2 plus ions catalyze the reaction. So what I like to do with these is, when I'm teaching it, is to break down this redox reaction here into the two half equations. So I'm going to do that. So the first one is going to be S2O8, and that is going to get reduced to the sulfate ion. I need to balance that, put a 2 there. Now, balance for oxygens, we don't need to do it. No hydrogens to worry about in this half equation. We've got 2 minus on the left and 4 minus on the right, so we're going to have to put in 2 electrons there. Okay. Now let's do the iodide ion. So we've got 2 I minus ions. Now that's going to go to I2. Right. Now we've got no hydrogens or oxygens to worry about there, but we need to put 2 electrons on the right-hand side of that equation. Okay. Now, the way this catalyst works is these electrons are these electrons which are given away here. They're actually given away to the Fe2 plus ions. So I'm going to put the Fe3 plus ions here. Get rid of those electrons, they're gone. And if you give an electron to an Fe2 plus ion, you turn it Fe3, sorry, you turn it into an Fe2 plus ion. So you've got that there. And in this one, it's the other way around. Okay, so you're not giving electrons. These electrons are coming from 2 electrons, 1 from each Fe2 plus ion. And that on the right hand side, when they have given away an electron, they are obviously going to become Fe3 plus ions. So you've got that there. So that's how the ions work. And you can see that the Fe2 plus, the Fe3 plus don't undergo any permanent change there. They just flip back between the Fe2 plus and the Fe3 plus. All right. And how is this catalyst working? Well, it doesn't ask you this, of course, we've written the equations, but this SO2O8 and this thing, they don't need to, in order to exchange the electrons coming from the iodide to the peroxide of sulfate, they don't need to meet. They're passed on through the Fe ions as an intermediate. So they don't have to meet. Takes the electrons off one, gives it away to the other. Right, okay, so now shrink that. Okay, next question, 4.3. We'll give a reason why zinc ions, okay, why wouldn't they work? Okay, make that bigger, sorry. Why don't zinc 2+ ions work in that? The reason why is because zinc only exists as 2+ ions. They can't exist as 3+ ions. They don't have a variable oxidation state. So I would say that, and that's why they don't catalyze it. Right. Now here we have got an ideal gas equation calculation here. Right. So iron reacts with dilute hydrochloric acid to form iron chloride and hydrogen. Okay. Right. We've got 0.08 grams of that, and we have got 30 centimeters cubed of 1 molar hydrochloric acid. So one reagent is in excess. So we need to work out which one is in excess. So let's do the moles of the iron first. So the moles of Fe is going to be equal to the mass over the atomic mass of iron. So that is going to be equal to 0.998 over the AR of iron. It's 55.8. That gives us a value of 0.0178. All right, now let's do the moles of the HCl. That's equal to the concentration times by the volume. The concentration is 1, and the volume is 30 over 1,000.03, which is equal to 0.03 moles. Right, now we can see here that it is going to be the iron is in excess. This one is in excess because look, they react in 1 mole of iron reacts with 2 moles of hydrochloric acid. So we have got 0.03 moles of hydrochloric acid. So the max Fe that can react with, max moles of Fe, is going to be 0.03 over 2, 0.015, which is less than this value here. So not all of the iron is going to react. The iron is in excess. Now we need to work out the volume of hydrogen gas produced here. So we need to work out the moles of hydrogen gas. So the moles of hydrogen gas, well, look, 2 moles of this gives us 1 mole of hydrogen. So that is the moles of hydrogen we're going to make, 0.015. Okay, let's write that down there. .015. Right. So now we have to work out the volume of the gas. So we're going to use the ideal gas equation. PV is equal to nRT. We need to work out the volume. So rearrange that. We get V is equal to nRT over P. Right. Now we need to always, ideal gas is units is always the problem, isn't it? So we need to remember that this is in kelvins. 30 degrees C, what's that in kelvins? Well, 273 plus 30 is 303 kelvins. The pressure is 100 kilopascals. We can't leave that in here. We must put that into pascals. So that's 100 times 10 to the 3. Our volume will be in meters cubed over there, and we've got our value of R. So let's put the numbers in there. So we simply get V is equal to 0.015 multiplied by 8.31 multiplied by T 303 divided by the pressure 100,000 . do that in the calculator, we get a value of a value of, sorry, 3.77 times 10 to the minus 4. And the units are meters cubed. Our units are already okay. Right. Right. On to the next question, which is about reaction of ions in solution. Fe2 plus Fe3 plus ions in solution. Okay, so here's figure 2, shows the reactions of ions in aqueous solution. Okay, so we've got the hydrated, we've got the Fe2 plus ion here. We've got the Fe3 plus ion here. You leave the Fe2 plus ion out in air, it will oxidize. The oxygen will oxidize it to the 3 plus ion. Right, so now identify A and state its color. Right, how do these 2 plus ions react with carbonates? Now, they are less acidic, remember, yeah? These are less acidic than the 3 plus ions. And they're not sufficiently acidic to react with carbonate, which is only a pretty weak base. So you don't get an acid base, you just get a precipitation reaction occurring here. So it's fairly straightforward. You just get a precipitate of iron carbonate, iron 2 carbonate, FeCO3. And that is a dark green color. Now, the next question asks us about precipitate B, which is a bit more difficult, okay? So precipitate B, we're given an ionic equation for the reaction of the Fe3 plus ion with aqueous sodium carbonate. Right. So this actually is, we'll give you the formula of the B, I'll give you in a minute, yeah? Right. That acts as an acid and it loses 3 protons to become the uncharged thing. So I'm going to write down this as kind of like, not really a half equation as such, but you'll see what I mean in a minute. Right, so that's 3 plus. I'm going to show that it loses 3 protons, so it's now H2O3, OH3, and I'm going to put 3H plus there. Now the carbonate ions, I'm doing a different color here. So carbonate ions, they act as bases. They accept protons. Each carbonate ion will only accept 2 protons. By the way, this is the formula of precipitate B, and it's dark brown. Right, so each carbonate ion is going to accept 2 H pluses, and it's going to form carbon dioxide and water. So we've got the green equation giving away 3H plus, and the blue equation here are only accepting 2. So how we will make that balance, we've got to multiply this one by 2. So it's 6 protons altogether. And we're going to multiply this one by 3. So that becomes 6 protons as well. So the protons are going to cancel out from both sides. So if we do that, I'll just write the equation down in full here. So we're going to have FeH2O6 and we're going to need 2 of those, multiply by 2, and we're going to need 3 carbonate ions. The protons are going to cancel out, so I'm not going to put them in the equation. And that's going to give us, well, 2 FeH2O3 OH3 And that's going to give us, well, it's going to give us 3 carbon dioxides and 3 waters. And that is our balanced equation, sorry, 3 there. It's quite tricky to just balance that equation by trial and error. So that's why I kind of use the protons there to kind of help you balance it. It's a bit like balancing a redox equation with electrons lost and electrons gained. So this time, of course, not redox, it's acid base. So we're balancing it with protons lost and protons gained, but it's the same sort of idea. And that is our equation there. Right. Now, explain why aqueous solutions have a lower of the 3+. Yeah. Why do they have a lower pH than the 2+? Well, of course, each ion, central ion, I wouldn't write this in your answer, this is just to explain, it's forming dated bonds with these water molecules, yeah? Now, why are these protons, why are these protons like, why are these allowing, why can they be lost that as a proton? But it's because this positive charge is dragging, it's polarizing the water molecule and making it easier to lose that, making the bond weaker, if you like, between the O and the H. Now, why is the Fe3+ better at doing it than the Fe2+? Well, it's because it's got a higher charge. So my answer here, I would say the Fe3+ is more highly charged. So it's better at polarizing the water molecules. Which makes it easier for them to lose H+. So it's going to make it the solution more acidic. pH is going to be lower. Okay. Right. So now onto equilibrium. Okay, so fairly straightforward year 12, this first little bit here. State and explain the effect, if any, of a decrease in overall pressure. Right. If you decrease the pressure, you are going to favor, actually, Atelier tells us, it's going to favor the side. It's going to try, if you decrease, it's going to increase it side with the most gas molecules. Gas molecules on the left, you've got 3, you've only got 2 on the right, so it's going to push it to the left. So you are going to get less SO3. Okay, so you decrease the pressure, you'd expect to get less SO3 at equilibrium. Right, so now we've got the usual thing here. You've got a container with 2 gases, and then it tells you how much you've got at the start, how much you've got at the end, and you've got to work out basically well, we've got to work out the partial pressure of SO2. So that we need to work out the number of moles of SO2 in this. So we're going to construct our usual thing here where we put down, write down the equation. So we're going to write down the equation, which is SO2, 2SO2 plus oxygen goes to 2SO3. And I usually write down here, I usually write down start moles. I like to write down used up moles here. And finally, equilibrium moles. So read the question. It tells us what we got at the start. We've got 0.46 moles of SO2. And you mix that with 0.25 moles of oxygen. Read the question carefully. It's clear we have got 0 SO3 at the start. When equilibrium is reached, the mixture contains 0.18 of SO3. Okay, so what I would then say is, you've got 0.18 of SO2, sorry, of SO3, beg your pardon, it's wrong. Got 0.18 of SO3 there. So now, if we formed that many moles, 0.18 of SO3, that means we must have used up 2 moles of SO2, gives us 2 moles of SO3. So we must have used that many moles up. So I'm going to put 0.18 there. So how many moles of SO2 we got at the end? Well, you've got to subtract 0.18 from 0.46. That gives you 0.28 there. Think about the oxygen now. Well, if we've used up 0.18 of the SO2, for every 2 moles of SO2, we only use 1 of oxygen. So that's a half of that. So that's 0.09 of oxygen we've used up. So how much oxygen have we got left over? 0.25 minus 0.09, that gives us 0.16 moles of oxygen. So we've got the number of moles of each gas now. We need to work out the partial pressure. So we need to work out the mole fraction of the SO2. So we need to work out the total number of moles at equilibrium. Write this down on the side here because we're running out of room a bit. Okay, so total moles at equilibrium, that's equal to 0.28 plus 0.16 plus 0.18. That gives us a total number of moles of 0.62. So the mole fraction, we're working on SO2. I'm going to use this lambda for mole fraction. Okay, so mole fraction SO2 is equal to the moles of SO2 over the total moles. Moles of SO2 we've got there is 0.28 over 0.62. That gives us 0.452. Right. Now we have now got to work out the partial pressure. So if you remember the equation for partial pressure of SO2 is going to be equal to the mole fraction of SO2 multiplied by the total pressure. So we've got 0.452 partial pressure of SO2 multiplied by the total pressure, which is scroll the question here. The total pressure is 215 kilopascals. Okay, so it's 215 times 215. That works out to be 0.452 times 215 gives us 97.1 kilopascals. Okay, right, 5.3. Right, a different mixture of SO2 and NO2 reaches equilibrium here, and given the partial pressure of each gas. So given an expression for the equilibrium constant Kp, and then work out its value and give its units. Okay, so Kp is going to be equal to the partial pressure of the products, which is SO3, and that's going to be squared because it's 2 moles of SO3, and that's going to be divided by the partial pressure of SO2. Multiplied by the partial pressure, and that's squared as well because there's 2 moles of SO2 in the equation, of O2. We don't square that. It's only 1 mole of O2. Put the numbers in. What do we get? We get right, SO3, right, that's 185, isn't it? Squared. Divided by that, well, that's 167 squared. Multiplied by that, which is 102. That is 0.012. That's the answer there. Now we need to work out what are the units of Kp. Well, all the pressures are given in kilopascals. So it's going to become some kind of derivative of kilopascals. Well, what we got on the top, we've got partial pressure of SO3, so that's kilopascals squared on the top. And then we've got the partial pressure of SO2 squared, so that's kilopascals squared there. And then we've got the partial pressure of O2, so that's just kilopascals. That cancels with that. So we get 1 over kilopascals as the units. Change the index sign of the indices to bring it up to the top. So it's kilopascals to the -1 is the unit there. Okay, what is the effect on the value of Kp if the pressure of the equilibrium mixture is increased? Now, this is a trick question because they want you to think, well, what happens if you increase? Well, first of all, just simply, the only thing that changes the value of Kp is changing the temperature. We haven't changed the temperature, so there is no effect. So it stays the same. They're trying to sort of make you think here, right? If you increase the pressure, you are gonna push the position of equilibrium that way. You're going to get a higher partial pressure of SO3, but that is not going to change the value of Kp. Kp doesn't change unless you change the temperature, which may seem a bit odd, but that's the case. Okay, now I think I'm going to end that video there, and I will carry on with question 6 in the next video.